Hi, this is John Carney, Product Engineer at Cadence, and this video is going to show you some solutions that will allow you to reduce the EMI on your PCB design. Electromagnetic fields on PC boards exist between any two conductors, such as a microstrip over a return plane. Current flows in loops and must have an uninterrupted path back to the source. If this return path is broke, the electromagnetic field will latch on to the next closest metal and will not likely be the return path you want. It will leak throughout the dielectric and cause common mode currents to flow all over the board, as well as cause cross-coupling of clocks and other high-speed signals. Let me walk you through how to use the return path constraint and DRC checks to find and fix these problems while you're doing your design. Say high-speed design, and let's take a look at this particular bus called PPA. First thing I want to do is I want to kind of highlight that bus and find in the design. So I'm just going to use the net navigator here to highlight the bus. I'm going to use this color wheel right here to select a color that I want to assign to the bus. I'll choose light blue. Now you could also click your right mouse button over here and pick a color if you want. So now that that bus has been selected and highlighted, if you want, you can also use different display modes. For example, you could put it into the ultra shadow display mode. So now you can see that blue really stand out with respect to everything out in the design. And if you want to, instead of seeing the color that you assign to it, see the layers that those different traces and vias exist on, you can use this toggle button here. And now the net is selected and highlighted, but it's highlighted in its layer colors instead of the color that you assigned for the net. So those are just a couple different ways that you can pick a net, highlight a net so you can see where it's at in the layout. With that net selected, you can use the docked constraint panel and go into the electrical category here. So in this docked constraint panel, you have the ability to specify all sorts of rules. We're going to be focusing on the electrical category here. Switch to the advanced mode, which gives you the option to constrain all sorts of advanced electrical rules like wiring, diff pair, delay. In this case, we're going to choose return path. And then you can assign a particular rule set that may already exist. And I'll show you how to make one in just a second. So once you assign a rule set, it's going to populate that rule set with the different controls for this constraint. So for return path constraint, you're specifying the reference net. So example, you want this net or this entire bus to reference the ground net. You specify the reference layers, whether you want it to be a closest plane layer, which is the closest plane in the stack up, a dual plane, which is looks for one above and below, or you can choose a table. This table lets you more explicitly control what the reference layer is going to be for every signal layer in the design. So you could say for layer 1, you want the reference layer to be layer 2 ground. For this signal layer, you want the reference to be layer 8 ground. Okay? So you can have a lot of control over what ground and what layer it's looking for it on. Then you have some other controls of length ignore. This is how long that trace can go without referencing that ground plane before you get a DRC. And then you have a pad gap as well, which tells you how big of a gap you can have around the pad, typically on surface layers, again, before you get a DRC. You can even specify how far away from the signal you need to have a stitch via and how close a void needs to be, or how far away a void needs to be before you get a DRC. So once you have those rules in place, you will then get dynamic real-time DRCs while you're routing. With that constraint in place, you're always going to have real-time DRCs while you're routing a design. For example, let's say you need to slide this trace over. Slide it over. Notice on the right-hand side, you're also getting heads-up display for other electrical constraints like propagation delay and relative propagation delay. So you're sliding this trace over because you want to try to adjust those delays. You slide it over, you drop it, and look at that. Lo and behold, you got a DRC. This DRC is telling you that it is a return path violation. You can also see that from the properties panel. From all the electrical constraint DRCs here, you can always use this pie chart here to browse the DRCs. So if you wanted to select the electrical category, double click on it. Once you double click the electrical category, it's going to break it down into 3 subsections. So if you want to see where the return path DRC are at, you can click on this square, or you can select the section of the pie chart. And then the search table down here is going to show you all of the return path DRCs that you can navigate through the design. This particular one is made because if you were to turn on the ground layer, there's a large void placed in the ground layer. I just added that for demonstration purposes so you can see how this return path violation DRC is calculated. So this trace is supposed to reference this ground shape. It's not, so therefore you get a return path DRC. Now let me show you how to accomplish the same thing using the constraint manager. So under the electrical domain, under return path, here you can see all the different electrical constraint sets. And here's an electrical constraint set called PP DDR4 ADDR. And this has the reference net of ground, the reference layer of closest plane, length of NOR, max pad gap. Exact same thing that I just showed you in the dot constraint panel. Then if you go into the net category, you can see you have this bus here. And for the reference electrical constraint set, you can assign that constraint set. Once you assign that constraint set, it's going to analyze and calculate it based upon what's routed in the design. And so then you can see the numerical values for all the violated constraints.